They say space sleeps. Every so often a stir breaks the silence. In November 2025, astronomers captured an image of 3I Atlas that stopped routine observation and forced hard questions. A faint interstellar visitor, the sort of speck we expect to drift through the planets, swelled in appearance by orders of magnitude. Where a compact halo once showed, twin streams of luminous material unfurled sunward and a single colossal tail stretched outward across millions of kilometers. Nothing in standard comet physics predicts jets that hold shape across those distances. Harvard astronomer Avi Loeb studied the data and posed the most uncomfortable option. Maybe this object formed by design rather than by chance. Stay with this narration until the end. The thousandfold growth might be phase 1 of something we never planned for. On November 9, 2025, two amateur astronomers in Germany pointed modest telescopes at a visitor labeled 3I Atlas. Frank Nebeling and Michael Buchner used a 140mm refractor and an ACI 6200 camera. They stacked 5 3-minute exposures and discovered enormous jets crossing their field of view. Structures so massive they stopped simple explanation. This marked the third confirmed interstellar object observed by humanity. The first, 1I Oumuamua in 2017, launched years of debate. The second, 2I Borisov in 2019, behaved like a typical comet. 3I Atlas arrived in July 2025 as a faint smudge moving on a hyperbolic track. By November the picture changed. The jets in the ground-based stack measured roughly 10 arc-minutes toward the Sun and 30 arc-minutes away from the Sun. At a distance around 326 million kilometers from Earth, those angles mapped to astonishing physical lengths. Sunward streams reached about 950,000 kilometers. Anti-sunward jets extended near 2.85 million kilometers. For scale, the solar diameter sits near 1.4 million kilometers. These streams rival whole planetary scales. This expansion did not look gradual. The structure seemed to balloon and hold coherence across regions where solar wind physics indicates quick shredding. Standard comet physics explains jets as volatile ices sublimating under solar heating and blowing dust outward. Sunward-pointing features sometimes appear as projection anomalies. Thin dust sheets along the line of sight can produce apparent inward-pointing structures. Those geometrical tricks do not match the three-dimensional, columnated appearance seen here. The orbital path adds more oddness. 3I Atlas follows a hyperbolic orbit unbound to our Sun with eccentricity above 1. Yet the orbit lies nearly in the ecliptic plane within 5 degrees. Random interstellar arrivals should come from all directions. The probability for such ecliptic alignment by chance rests near 0.2%. Mass estimates deepen the puzzle. Based on brightness and assuming typical comet albedo, the nucleus likely measures at least 5 to 10 kilometers across. That size towers over earlier interstellar visitors. If the density approximates half a gram per cubic centimeter, the mass moves into tens of billions of tons. Population models for interstellar objects make encountering such a massive body inside the inner solar system inside a single decade astronomically unlikely. Faced with those numbers, some researchers, including Avi Loeb, asked if a natural explanation could survive scrutiny. Others preferred to exhaust exotic natural mechanisms before exploring alternatives. The November 9th image forced the question into the open. A thousandfold increase in apparent size demands a response. Either standard comet physics fails dramatically at these parameters, or processing and observational artifacts produce a misleading picture, or something else operates. The imaging needs careful examination. Amateur contributions provide crucial rapid follow-up, and wide-field coverage professionals cannot always match. But stacking multiple exposures introduces risks. Misalignment, scattered light, internal reflections, and ghost images can produce false structure. The fact two independent setups captured similar features strengthens the case for reality. Still, higher resolution space-based confirmation remains essential. The jets are present in the data. Whether the jets represent physical columnated streams spanning planetary distances or a combination of dust sheets, projection effects, and processing artifacts requires more observation. If the jets are genuine, the physics breaks. Consider outgassing velocities. Typical comet gas speeds hover near 0.4 kilometers per second at several astronomical units. At that speed, material requires roughly 30 days to reach 950,000 kilometers and about 70 days to reach 2.85 million kilometers. Time since discovery and passage near perihelion allows those timescales. The sticking point arises from solar wind erosion. The solar wind streams outward near 400 kilometers per second. When that supersonic plasma hits slower cometary ejector, it exerts strong ram pressure. To hold a narrow jet against such a flow, the jet density must exceed surrounding solar wind by many orders of magnitude. Ballpark estimates place required density near 1 million times greater. That implies mass loss measured in billions of tons per month. A nucleus 5 to 10 kilometers across lacks a sustainable reservoir for that loss without clear non-gravitational acceleration. Yet astrometric tracking shows no obvious strong recoil. The contradiction stands. Anti-sunward jets that appear sunward create a separate paradox. Radiation pressure and the solar wind both push material outward from the sun. Inward-pointing features usually require a projection effect or very specific electromagnetic coupling of charged dust with magnetic fields. Projection scenarios work for short-lived features. Electromagnetic guidance operates on small scales near the nucleus. Scaling those effects to millions of kilometers demands magnetic fields or charge distributions far beyond known cometary environments. Scientists split into 3 camps. The first accepts an extreme natural comet hypothesis. Here the nucleus hosts unusual composition and structure. Hypervolatile ices such as carbon monoxide or nitrogen could sublimate at lower temperatures and eject material at higher speeds. Electromagnetic effects might produce narrow initial collimation. A combination of hypervolatile chemistry, crustal insulation created by cosmic ray processing, and favorable viewing geometry could plausibly generate outbursts and persistent streams. This position preserves known physics and only extends parameters into edge regimes. The second camp emphasizes imaging artifacts and transient projection phenomena. Stacking misregistration, scattered sunlight, atmospheric turbulence, and incomplete star subtraction can produce false jets. Differences between July Hubble imaging and November ground-based stacks raise legitimate caution. Independent high-resolution imaging, preferably from space, would settle the question. Processing subsets of the data, examining single exposures, and testing multiple stacking algorithms provide practical ways to validate the signal. The third camp presents a technological interpretation. If the object operates under artificial propulsion principles, then exhaust velocities shift the mass budget dramatically. Ion drives and plasma thrusters produce exhaust at tens to hundreds of kilometers per second. Higher exhaust velocity reduces required mass flow to produce observed momentum. Momentum flux scales with mass flow rate times velocity. For example, ejecting material at 30 kilometers per second requires much less mass than at 0.4 kilometers per second to match observed momentum. Artificial propulsion thus makes the observed coherence against solar wind plausible with a manageable propellant inventory. Exhaust plumes aimed toward the sun explain sunward-pointing jets through straightforward mechanics. In that scenario, anti-sunward and sunward streams correspond to thrusting geometry. This technological hypothesis requires definitive signatures. Spectroscopy should reveal propellant species. Ion thrusters use xenon or krypton. Chemical rockets involve hydrogen, oxygen, or other molecules. Narrow spectral emission lines associated with ionized propellants would present a strong case. Non-gravitational acceleration consistent with directed thrust would offer another smoking gun. To date, neither unambiguous propellant spectral lines nor compelling thrust signatures appeared. The argument turned on testability. If artificial, spectroscopy, Doppler velocity mapping of jets, polarimetry, and astrometric monitoring will reveal telltale patterns. If natural, those same measurements will align with cometary expectations. Let's parse the numbers. Magnetic confinement requires ionized plasma fractions and field structures strong enough to pinch flows across huge distances. Electrostatic lofting lifts charged grains off surfaces under ultraviolet irradiation and interactions with solar wind electrons. both operate under known physics on small scales. Scaling them up requires extreme parameter choices. Hypervolatile chemistry offers higher ejection velocities and delayed thermal response. Delayed heat conduction into volatile reservoirs can create outbursts well after perihelion. Ion tails and plasma sheaths produce narrow, faint structures under solar wind magnetic guidance. Each mechanism explains partial aspects of the November morphology. Stacking multiple mechanisms yields a composite natural model. That model demands several rare conditions to align. Opponents argue stacking epicycles reduces explanatory elegance. Proponents reply that nature frequently surprises when new parameters or environments appear. History offers a guide. When 1Oumuamua arrived in 2017, the discovery produced rapid, polarized debate. The object displayed slight non-gravitational acceleration while lacking a visible coma. Some researchers proposed a radiation pressure-driven sail hypothesis. Others developed hydrogen or nitrogen iceberg models. None of those alternatives proved decisive given sparse data. The episode highlighted limits that arise when detection happens late and follow-up time stays short. Institutional risk also surfaced. Scientists who proposed unconventional hypotheses faced reputational costs. Media sensationalism amplified contentious claims while nuance evaporated. The lesson lives in two parts. Detect interstellar objects earlier. Assemble follow-up plans quickly. Preserve scientific rigor while permitting unconventional, testable ideas. For 3I Atlas, the observation window matters. The object passed perihelion on October 13, 2025 and approaches a favorable Earth distance on December 19, 2025. That date offers optimal conditions for high-resolution spectroscopy and imaging. Observations across the electromagnetic spectrum must proceed during the coming weeks. Priority measurements include high-resolution spectroscopy for molecular and ionic identification. Detecting xenon, krypton, or unusual isotopic ratios would indicate propulsion exhaust or synthetic materials. Doppler mapping of jets yields velocity profiles. Distinguishing slow sublimation speeds from tens of kilometers per second exhaustion tests the core physics. Polarimetric imaging reveals dust particle size distribution and composition. Astrometry tracks non-gravitational acceleration. Time series imaging documents morphological evolution. A pattern of discrete pulses or deliberate orientation changes would suggest propulsion. Smooth, rotation-tied jets favor natural explanations. Amateur astronomers will remain essential. Professional facilities provide unmatched sensitivity. Space telescopes like JWST and Hubble offer decisive calibration advantages. Yet amateurs provide continuous coverage and rapid response. The November 9th image arose from skilled amateurs executing careful stacking. Their role proves crucial for anomaly detection. The scientific community must balance skepticism with respect for grassroots contributions. Independent verification using different equipment and processing pipelines remains the gold standard. Beyond optics, radio, and transient detection networks contribute. The Global Gravitational Wave Observatory Network and the operational culture built for rapid multi-messenger follow-up demonstrate how to mobilize across instruments. LIGO and partner detectors transformed reaction time. Alerts now trigger coordinated campaigns. Adapting those protocols to interstellar object anomalies offers benefits. If 3I Atlas emits transient electromagnetic signatures or displays sudden morphological changes, rapid multi-wavelength response will capture ephemeral signals. Radio astronomy offers unique tests. Fast radio burst detection pipelines and machine learning tools trained on massive data streams identify millisecond transients and reject human interference. If an artificial system near 3I Atlas emits intermittent radio bursts, existing FIB-like pipelines could flag these events. Historically, radio searches of comets targeted specific molecular lines. Broadband, transient-oriented searches rarely occur. Adding such searches to observing campaigns remains low cost and high reward. JWST provides vital chemical constraints. August JWST data already indicated an irradiated crust and elevated carbon dioxide relative to water. Infrared spectroscopy yields molecule fingerprints and isotopic ratios. JWST's sensitivity enables detection of trace species. Searching for signatures inconsistent with natural comet chemistry offers direct testing. The prior phosphine detection in a brown dwarf showed how new instruments overturn assumptions. JWST recorded unexpected molecules once unavailable to prior telescopes. The presence or absence of propellant ions or synthetic compounds around 3I Atlas will narrow hypotheses decisively. Image processing requires caution. Stacking algorithms align frames, suppress noise, and highlight faint structures. Misalignment and star subtraction errors introduce artifacts. Scattered sunlight inside optics creates ghost images. Cosmic ray hits produce spurious pixels. Atmospheric turbulence smears features. The rigorous test involves examining single exposures for persistent structure, reprocessing frames with alternate algorithms, and seeking confirmation across observatories. Polarimetry and wavelength diversity offer further discrimination. Real dust produces polarization patterns. Optical artifacts generally do not. The social dynamics around anomalous discoveries matter. The Oumuamua episode revealed how reputations, career incentives, media behavior, and the amateur community interact. Scientists who propose contrarian ideas risk professional backlash. Journals and peer review function as gatekeepers. Media outlets favor sensational headlines. Social platforms amplify the most dramatic interpretations. Those dynamics shape how the public perceives the science. Transparency helps. Faster calibrated data release paired with clear caveats reduces rumor. Professional engagement with forums and citizen scientists fosters constructive collaboration. Science benefits when professionals support amateurs with guidance on photometry, spectroscopy, and error analysis. That guidance turns early hints into robust results. Conspiracy accusations follow anomalies. Delays in data release create suspicion. Agencies embargo raw observations to allow proposers time for analysis. That policy protects scientific priority but raises transparency concerns when public attention runs high. A balanced approach involves releasing preliminary calibrated data with clear metadata and caveats. That practice reduces misinterpretation while preserving scientific rigor. AI shapes detection and discourse. Advanced models process enormous datasets for transients. Machine learning finds patterns in radio streams, optical surveys, and archival records. Automated pipelines accelerate FIB discovery. Adapting these algorithms for anomaly detection across wavelengths raises the probability of catching unexpected signals. AI also enables realistic visualizations and synthetic imagery. Generative tools make photorealistic renderings trivial. The risk of fabricated space images increases. Provenance, metadata verification, and raw data access become essential defenses. Media dynamics shift with AI. Automated article drafting and headline optimization favor shareable narratives. Sensational frames proliferate. Scientists who communicate clearly and promptly reduce room for distortion. Those who avoid public engagement leave the field to speculative voices. Responsible outreach requires concise statements emphasizing methods and uncertainties. Share raw data when feasible. Invite scrutiny. The broader observational landscape evolved rapidly by 2025. Gravitational wave observatories ran observing Run 4 through mid-November, increasing detection rates and improving coordination. Radio arrays and fast transient pipelines identified FRBs by the thousands. JWST provided chemical detail inaccessible before. AI systems processed petabytes in real time. These capabilities converge to create an unprecedented toolkit for anomaly investigation. As the December 19th closest approach gains proximity, the scientific plan sharpens. Observers will deploy high-resolution spectrographs, polarimeters, radio transient monitors, and astrometric trackers. Campaigns will search for xenon, krypton, unusual isotopes, narrow emission lines from ionized species, and non-gravitational trajectory deviations. Teams will compare single-frame images against stacked results. They will reprocess datasets with diverse pipelines and check for consistency across geographic locations and instruments. Time series will record jet morphology changes hourly, daily, and weekly. If jets pulse with periodicity matching a rotation, or if thrust pulses align with systematic acceleration components, results will push interpretation toward propulsion. If spectra show only water, carbon dioxide, and known cometary species with mass loss rates tied to solar heating and no directed acceleration, the natural extreme comet hypothesis gains weight. The stakes remain immense. If analysis confirms exotic natural physics at work, this will force rethinking of interstellar object populations, ejection mechanisms in planetary formation, and the limits of cometary behavior. If artifacts explain the November image, the episode will reinforce the need for rigorous validation of surprising signals. If tests show artificial propellant signatures or controlled thrust, the discovery will stand among the most consequential in human history. The pathway to resolution relies on measurements. Spectroscopy, Doppler mapping, polarimetry, astrometry, and time series imaging provide direct tests. The scientific method remains the arbiter. Public discussion will not pause while scientists collect data. Social media, forums, and news outlets will continue to spin explanations. Conspiracy narratives will emerge and evaporate. The professional community must balance caution with accessible communication. Provide data. Explain uncertainty. Invite amateur collaboration. Resist premature conclusions while acknowledging the extraordinary nature of the observations. A final practical note. Archival searches and AI-driven anomaly scans matter. Reanalyzing prior surveys with modern algorithms sometimes uncovers missed signatures. Apply FIB-style pipelines to historical radio recordings around the object's position. Mine optical archives for subtle transient features before Nebbeling and Buchner's November detection. Cross-match datasets across wavelengths. If 3i Atlas left faint markers earlier, those traces may already sit unnoticed in archives. The universe has a long memory. Human observation is short. Each new instrument enlarges the window. JWST, gravitational wave networks, radio transient arrays, and AI form a web of sensors ready to catch the curious and the rare. For now, 3i Atlas drifts through a narrow window where human eyes and instruments reach. Teams will gather data in the coming weeks and months. The answers will arise from spectra and motion, from polarization and timing, from careful reprocessing and cross-validation. Whether the visitor proves to be an extreme natural object, an optical artifact, or a crafted machine, the process of testing hypotheses will expand knowledge. Sit with the mystery. Watch the telescopes. Read the spectra as they arrive. Expect ambiguity and correction. Science advances through iteration. The next chapters will show how rigorous measurement handles an extraordinary observation. Whatever outcome emerges, the enterprise of observation will grow stronger. Humanity stands prepared to measure, test, and revise. The universe will reveal more if we keep asking the right questions and follow where the data lead. Under the clear November skies of 2025, telescopes across the world turned toward a point of light that refused to behave. 3i Atlas, a faint, unremarkable interstellar wanderer, had grown into something that made even veteran observers uneasy. In a matter of months, its faint halo had transformed into a system-sized storm of light and dust. Astronomers knew the numbers too well. A halo 950,000 kilometers long on one side, nearly 3 million on the other. It stretched wider than planets. It should have fallen apart instantly under the pressure of the solar wind. But it didn't. It held together, coherent, luminous, and silent. 4 days after the first stacked images circulated, observatories from Chile to Japan tried to confirm them. Some saw faint traces, others saw nothing. Online forums filled with speculation. Were the German amateurs seeing genuine structure, or had the stacking software built a ghost from noise? Then came the first confirmations from independent observers using larger instruments. The jets were faint, but they were there. The object had changed. Every explanation clashed with known physics. Volatile ices should sublimate evenly across the sunlit surface, producing diffuse comas, not narrow columns that stay focused over millions of kilometers. The energy budget didn't balance. The solar wind should have shredded the columns within hours. Astronomers tried the most conservative possibilities first. Maybe the nucleus was rotating fast enough to focus outgassing into thin plumes. Maybe magnetic interactions confined charged particles into filamentary streams. Each fix required pushing numbers to extremes. Magnetic fields stronger than any measured around a comet, outgassing rates thousands of times higher than typical. None of it quite worked. The longer the object stayed bright, the harder the explanations became. The jets seemed to pulse, brightening and fading in cycles of several hours. The orientation of the plumes didn't match expected rotation. Some pointed almost directly toward the sun, some at sharp angles to the orbital path. And through all of this, the nucleus remained unresolved, a single point, bright but featureless, even to Hubble. On December 1st, data from an infrared observatory in Chile added another layer. The spectrum showed carbon dioxide, yes, but in quantities far above standard comet ratios, and barely any trace of water vapor. That meant the outgassing wasn't driven by sunlight heating surface ice. Something else was energizing it. Avi Loeb wrote a brief note the next day. When natural explanations strain against the limits of known physics, the correct response is not panic. It's measurement. And measurement became the mantra. Telescopes queued up across continents. The JWST observations in early December focused on spectroscopy. They looked for xenon and krypton emission lines, the kind associated with ion propulsion exhaust. None appeared above detection thresholds, but one narrow feature near 672 nanometers puzzled analysts. It didn't match known cometary lines. Calibration errors couldn't account for it. The signal appeared again in a follow-up observation 2 nights later, slightly shifted, as if moving with the object. The data weren't public yet, only a few researchers had access, but leaks traveled fast. Threads on astronomy forums filled with speculation. Propulsion exhaust, plasma emission, or an unknown molecular fragment created by cosmic ray bombardment. The narrative split into 2 currents. One group pushed deeper into natural physics, arguing that hypervolatile ices like nitrogen or methane could explain the features. Another insisted the evidence hinted at something engineered, maybe an ancient derelict using decaying systems that sporadically vented. Neither side had proof. Both had equations. Mid-December brought an avalanche of new observations. Radar pings from planetary defense networks bounced faint echoes off the object, enough to suggest a roughly spherical shape 5 to 10 kilometers in diameter, larger than initial estimates. Light curve analysis revealed a slow rotation, about 9 hours per turn, that ruled out rapid spin focusing the jets. Then, 3 days before closest approach, an anomaly appeared. Precise astrometry showed a minuscule but consistent deviation from the projected gravitational track, a drift of about 10 meters per second over 48 hours. Too small for spacecraft propulsion, but larger than expected for random outgassing. Natural? Possibly. Intentional? Harder to say. When the closest approach came on December 19th, the world watched live streams from observatories. 3i Atlas glowed faintly against the backdrop of stars, its jets visible even through mid-sized telescopes. The object passed uneventfully, silent and steady, continuing its outbound course. Yet the data left everyone with more questions than answers. Weeks later, as the raw telemetry poured in, research groups divided tasks. One team worked the spectral data, another the astrometric anomalies, another ran plasma interaction models. The spectroscopy team confirmed no classic propellant ions, but also found ratios of carbon monoxide to carbon dioxide inconsistent with any known comet. The astrometry team verified the small acceleration but couldn't attribute direction precisely. It varied unpredictably, not aligned with the jets. Plasma modeling showed that under specific conditions, a weak magnetic confinement combined with heavy ionization, a comet could maintain narrow jets. But those conditions required densities and field strengths never observed. In early January 2026, NASA released a formal statement. Current data support a natural origin for 3i Atlas, though with properties extending beyond existing cometary models. Additional observations are ongoing. It was a cautious verdict, neither confirming nor denying the extraordinary. Behind the official tone, debates continued. Some astronomers privately admitted the data felt staged by the universe to taunt them. Every measurement plausible yet implausible, every anomaly explainable yet not fully explained. Meanwhile, the object dimmed, receding into the outer system, past the orbit of Jupiter by spring. The jets faded. The mystery cooled with distance. But the social wake continued to ripple. Amateur astronomers, energized by the November discovery, formed ad hoc global networks to coordinate observations of new transients. AI tools filtered sky surveys nightly, flagging faint moving points that might be future interstellar visitors. Universities began drafting proposals for rapid response funding, small grants deployable within days of detection rather than months of review. The Oumuamua lesson had been clear: catch anomalies early. 3i Atlas reinforced it with force. Public fascination didn't fade. Videos about the alien probe that passed us by racked millions of views. Some treated the idea as fact, others as myth. The truth lived in gray. Scientists appeared on podcasts and news panels, trying to reset expectations. An anomaly doesn't imply design, they repeated. But neither should we fear asking why something breaks our models. Still, the online space filled with noise. Deepfake videos showed fabricated close-ups of the object, complete with glowing engines and metallic reflections. AI-generated leaks of supposed NASA documents circulated. Distinguishing genuine data from invention became work in itself. Professional astronomers responded by building public data repositories. Raw images, calibration files, and reduction scripts became open access. Verified authenticity replaced authority as the currency of trust. By mid-2026, the academic papers began to appear. One modeled the jets as magnetically confined plasma flows triggered by ion-dust interactions. Another proposed delayed thermal waves penetrating an insulating crust, releasing gas in periodic bursts. A third paper argued for rotational instability exposing buried volatile pockets. Each explained parts of the puzzle. None covered everything. Avi Loeb published a summary essay titled "The Question is the Answer." In it he wrote, "The universe may not owe us clear categories of natural and artificial. The distinction could collapse when physics reaches complexity indistinguishable from design." Critics called it philosophy disguised as astrophysics. Others called it preparation for what comes next. In parallel, the technological landscape that surrounded astronomy evolved rapidly. The AI systems built for FIB detection migrated into optical data streams, sifting terabytes nightly for transient events. Some of those algorithms began flagging strange short-duration optical flashes near known cometary bodies, tiny bursts lasting seconds. Most turned out to be cosmic rays, satellites, or noise. But a few resisted easy classification, inviting further study. The infrastructure created for gravitational wave follow-ups became standard for every kind of transient. When a telescope reported an anomaly, automated notices fanned across observatories, mobilizing within minutes. 3i Atlas had seeded a culture of vigilance. And yet, as more anomalies were caught, the extraordinary began to feel routine. The public's appetite dulled. Each new discovery drew fewer headlines. The era of wonder had given way to an era of verification. In autumn 2026, long after 3i Atlas had faded beyond Saturn's orbit, a reanalysis of archived data reignited interest. An AI pipeline trained for transient plasma emissions detected a faint, repeating radio signature in observations from the Allen Telescope array dated November 17, 2025, 10 days after the German image. The pattern lasted 2 minutes, repeating at regular 1.7-second intervals before vanishing. The frequency sat near 8.4 GHz, a band commonly used for spacecraft telemetry. Analysts checked for satellites, aircraft, radar, nothing matched. The signal was weak, barely above noise, and never repeated. Most scientists dismissed it as coincidence or terrestrial interference. but a few quietly pointed out the timing overlapped with the period when 3I Atlas showed maximum jet brightness. The data weren't conclusive, only provocative. Another mystery layered on the first. By early 2027, the object had drifted beyond detection range of optical telescopes. It became a line of numbers, coordinates, velocities, fading magnitudes, in data archives. Yet the changes it triggered in practice endured. Observatories established a standing interstellar object task group combining optical, infrared, radio, and plasma researchers. New software could automatically simulate trajectories for potential interstellar origins within minutes of discovery. Amateur observers received standardized processing pipelines to reduce artifact risks. Open repositories logged every exposure with full metadata to prevent misinformation. The next object would not catch humanity by surprise. A year later, in March 2028, the Pan-STARRS array flagged another hyperbolic object. Smaller, dimmer, moving fast. The alert spread instantly through the networks built after 3I Atlas. Telescopes turned, algorithms paused, spectrographs queued. Within hours, preliminary data showed nothing extraordinary, a small, cold, reddish body with a simple coma. But still, the machinery moved flawlessly. The lesson from 3I Atlas had hardened into habit: observe first, argue later. In retrospect, historians of science might call 3I Atlas the object that professionalized anomaly response. It forced astronomy to reconcile curiosity with caution. It showed how amateurs and AI, professionals and institutions, could form a single sensing organism. It exposed the fault lines of scientific culture, reputation, funding, media pressure, and in doing so strengthened them. Was it natural? Probably. Was it unique? Certainly not anymore. The galaxy is full of wanderers crossing interstellar space. Some carry ordinary chemistry, some carry surprises. None require intention to astonish. But every so often, one reminds us that the unknown still visits. And when it does, telescopes open, algorithms hum, people across the planet lift their eyes from screens to the sky. They measure, they question, they argue, and for a brief window, before certainty closes in, humanity once again feels the weight of the cosmic silence, not empty, but waiting.